Hi, this is Alex from devstories.eu. NumPy, Episode 3 of 7. You have a matrix of 1 billion pixels, and you need to flip its rows and columns. If you do this in standard Python, your machine will grind to a halt while it copies gigabytes of data. In NumPy, this operation happens instantly. Reordering those pixels does not actually move a single byte of memory. This happens because of how NumPy handles memory, strides, and views under the hood. To understand why NumPy is so fast, you have to look at the internal structure of an array. A NumPy array is not a single monolithic object. It is strictly separated into two pieces. The first piece is the data buffer. This is a contiguous, flat block of raw memory. It is just a one-dimensional line of bytes sitting in RAM. The raw buffer knows absolutely nothing about rows, columns, or dimensions. The second piece is the metadata. This is a small header, implemented internally as a C structure that tells NumPy how to interpret that raw line of bytes. The metadata holds a pointer to the start of the data buffer, the data type, the shape of the array, and the strides. Strides are the mechanism that transforms a flat line of memory into a multidimensional grid. A stride is simply the number of bytes the computer must step forward in memory to find the next element along a specific axis. Suppose you have a two-dimensional array of 64-bit integers. Each integer takes up 8 bytes. To move one column to the right, the stride might be 8 bytes, but to drop down to the next row, the stride might be 80 bytes because it has to skip past an entire row of data in the raw buffer to find the start of the next one. Many developers assume that when you take a slice of an array, the system allocates new memory and copies the selected data over. That is incorrect. When you request a slice, NumPy leaves the raw data buffer completely untouched. Instead, it creates a new metadata header. This new header points to the exact same block of memory, but it changes the starting pointer and modifies the strides to skip the elements you excluded. This is called a view. Here is the key insight. Because the raw data and the metadata are kept separate, operations that change the shape or order of the array are almost completely free. Think back to transposing that massive billion-pixel matrix. NumPy does not pick up the data and rearrange it physically. It simply swaps the stride values in the new metadata header. The number of bytes you used to skip to find the next row becomes the number you skip to find the next column. A completely different array structure is returned to your code, but it is just a view looking at the exact same physical memory. This separation is the foundation of NumPy's memory efficiency. You can carve a massive dataset into dozens of overlapping slices, pass them into different functions, and consume zero extra memory for the data itself. You are only generating tiny metadata headers. However, this means you share state. Modifying a value in a slice will alter the original array because there is only one true data buffer beneath them all. The separation of raw bytes from the rules that govern them means your heaviest data transformations are often just lightweight metadata swaps. That's all for this one. Thanks for listening, and keep building.